So this is problem number 1 on workshop number 6. So the biggest thing when you get questions like this, you got to look at those 4 factors. What are the 4 factors? The electrophile, the nucleophile, the leaving group, and the solvent. So what I've done here, at least one of these we can just like essentially cross out. So I haven't actually shown any solvents. So that's kind of just a non-thing. Right? It's a non-starter. The electrophile here is what? So the electrophile is actually the same for all of these. And what kind of electrophile is this? What kind of electrophile do we have? It's a secondary, and it's allylic. Right? So you got to be able to identify the electrophiles. It's secondary because this carbon is bonded to 1 hydrogen. If it was bonded to 2 hydrogens, it'd be primary. If it was bonded to no hydrogens, it would be tertiary. But this is not just secondary, right? It's secondary because of that, but it's also next to a pi bond. Just a pi bond. That means it's secondary and allylic. If it was a benzene ring here, it'd be secondary and benzylic. This is secondary and allylic. So looking at the electrophile, secondary and allylic, does that eliminate any of our mechanisms? SN2, SN1, E1, E2. Does that eliminate anybody? Secondary allylic is possible for all of those. So that's consistent, though. That's actually helpful. That's consistent. Right? So that's not changing. That means I don't have to, do you have to look at that factor anymore? No, you don't have to worry about it. It's the same. So so that's kind of checked off. Is the leaving group changed in any of these? Or is the leaving group the same? It's the same. Right? So is that going to be a factor we're going to need to worry about? No, right? So again, it doesn't change. So we've essentially, in this problem, we've isolated the nucleophile as the only factor that we're going to look at. And what matters for the nucleophile in these reactions? How reactive it is and what its size is. Reactivity and size. Reactivity and size. Right, these are the 4 factors. We went through this for every single problem. For SN1, SN2, E1, E2, we went through these 4 things. That's right. In this case, we're isolating just the nucleophile, and we're going to look at the reactivity and size. That's the important part about it. So, what do we remember? Reactivity. So reactive things are which ones? Which type of reactions want to be reactive of these 4 down here? Reactive nucleophiles are the charged, so that's SN2 and E2. They like the reactive nucleophiles or bases. E1 and SN1 want the less reactive ones. Okay? Who wants the small nucleophiles? SN1 wants a small nucleophile. What else? SN2. So green is small. Blue was reactive. Who wants large nucleophiles or bases? E1 and E2. And of course, unreactive would be, why not throw another color in to make this as confusing as possible? That would be unreactive SN1 and E1. So not charged. Okay, so now let's look at our possibilities. How would you describe this? Is it charged or uncharged? Charged, so is it reactive or unreactive? Okay, it's reactive, so that means it either has to be E2 or SN2. Is it small or big? Big. Who wants big? E2. So what kind of reaction is this one going to be? E2. We'll worry about the mechanism later and how that reaction actually works. We need to identify it now. Well, this next one, is this reactive or unreactive? Not charged, so it's probably unreactive. Is it big or small? So unreactive and small, what does that tell us? SN1. Next one down. Charged, so it's going to be reactive. Is this big or small? Small and reactive, that's going to be SN2. Last one, looks pretty big, unreactive. What's when this going to be? E1. Okay. So make it simple on yourself. Write down these 4 things as soon as you get the exam on Friday. Write down reactivity and size, we look for a nucleophile. Write down the types of electrophiles. Write down the types of leaving groups. Write down the types of solvents. You'll have it there. The answers lie within. But don't overcomplicate it, right? Isolate the factor. This is secondary allylic, that can be anything. Okay. Leaving group's the same. That can't be it. The solvent, we don't even have the solvent, so it's not even an issue. It's all, this case was all about the nucleophile. Isolate those factors and remember what's important. All right, let's take a look at one particular example, an E2 example. So we've decided this is an E2 reaction. It's secondary allylic electrophile. It's got a bulky reactive base or nucleophile. And we're going to do an E2. How many steps is an E2 reaction? 1 step, so it's concerted. We need things to be anti-periplanar. Now, it's not going to be an issue here because if we'll identify our beta hydrogens and we'll see it's not an issue. But the first thing you should do in any elimination reaction, right? In E1, once you form a carbocation, you think about rearrangements. And in an E2 reaction, you need to find your beta hydrogens. Beta hydrogens. Now, not all beta hydrogens work. It's a particular type of beta hydrogens we need to find. sp3 hybridized beta hydrogens, right? Beta hydrogens on sp3 hybridized carbons. So we need to find sp3 beta hydrogens. It's a little different. So for instance, if I start drawing all the beta hydrogens, which of course are 1, 2, right? This is the alpha carbon here. Beta carbon, beta carbon. The beta hydrogens are attached to the beta carbon. So if I start drawing these in, there's the beta hydrogen. And there's 3 beta hydrogens here. This is the alpha carbon. This is the beta carbon. There's 2 types of beta carbons. There's 2 types of beta hydrogens. Now, this beta hydrogen doesn't work though for E2 elimination or an E1 elimination. Why not? Because what's the hybridization state of that carbon? This doesn't work. So this is nice. How many types of beta hydrogens do I have here? Just 1. So how many different types of products can I make? Just the 1. Right? With E2, just the 1. E1 might be a little different, but with E2, just the 1. These are the only that matter. They're all the same. And we don't need to worry about things being anti-periplanar because there's 3 of these, and this bond rotates easily, right? It's a sigma bond, and it rotates. It's not in a ring. We don't need to do ring flips. We don't do anything like that. There's no stereochemistry. There's no wedges and hatches. So any one of these H's will work, right? I mean, it still has to be anti-periplanar, right? But it's not as big a deal if there's no wedges and hatches and if there's no rings constraining things. So do the anti-periplanar. So the first step, these beta hydrogens, you need to take that H, the beta hydrogen, sp3 beta hydrogen. That bond is going to break. 3 arrows. You eliminate, right, the leaving group. You form a pi bond. Balance my charge. Right, be careful to balance your charge. There's a Cl minus formed. Right, so make sure you balance your charge. And that's the only product you'll make from an E2 reaction in this case, because it only has 1 type of sp3 hybridized beta hydrogens. That's the only type only alkene product you're gonna make. So we have here all the different types of electrophiles possible. Same leaving group. I just kept it all as bromine, but all of this is to highlight primary, secondary, tertiary, primary allylic, secondary allylic, tertiary allylic, primary benzylic, secondary benzylic, tertiary benzylic. So how do I understand the term primary? Where does that come from? That comes from looking at the leaving group and the carbon it's attached to and how many hydrogens it's bonded to. So this first row, they're all primary. The carbon the leaving group is bonded to 2 hydrogens. So these are all primary. Now, they're a little different. This is primary. This is primary allylic. This is primary benzylic. The allylic comes from the carbon that's attached to the leaving group is next to a pi bond. That's the allyl group. The benzylic part comes from the carbon that's attached to the leaving group is bonded to a benzene ring. Still primary, right? The carbon that's attached to the leaving group has 2 hydrogens. But when that carbon is also attached to a benzene ring or a pi bond or an alkene, right, then it's either benzylic or allylic. Now these are different. These can form carbocations. Now why is it okay for this will never form a carbocation because there's not that many hyperconjugation buddies. If this form a carbocation here, there'd only be 3 hyperconjugation interactions. This is a primary, but when it forms a carbocation here, what can it do? It can do resonance. This pi bond can move over and help spread that charge out and stabilize it. And then a benzylic is even better. If you put a plus charge here, it's a primary carbon, but this whole benzene ring, all 3 of these pi bonds can help spread that charge out, make it even more stable. So this would be more stable than the allylic even. Benzylic would always be more stable than allylic. These other ones, so what's a secondary? Would mean the carbon that's attached to the leaving group is only bonded to 1 hydrogen. So these would all be secondary. Of course, this would be secondary and allylic, secondary benzylic. Now this carbocation would be more stabilized than this one, because this one has all the same resonance this has, but then it also has what? 3 more hyperconjugation buddies. Sigma bonds 2 bonds away. So this secondary benzylic would be even more stabilized than a primary benzylic. Yes? Now tertiary, notice how the carbon attached to the leaving group has no hydrogens bonded to it. So these would all be tertiary. Tertiary allylic. Tertiary benzylic. Tertiary benzylic is going to be more stable than a secondary carbocation benzylic or a primary carbocation that's benzylic, because this has 6 hyperconjugation buddies plus the benzene ring stabilizing it if it was forming a carbocation. Could you do an SN2 reaction on this? No, because it's still tertiary. You can't do SN2 reactions on tertiary. Why? Sterics. You can't get to sigma star. These get a little tricky, right, when you form carbocations, because these can do resonance structures. They're not rearranging. These are doing resonance structures. Now, here's an easy tip. Benzene rings are really stable. So the likelihood that this pi bond is really going to move is not that high. I mean, it's going to stabilize it, but it's going to actually not have a benzene ring at the end. It'll always have a benzene ring at the end. These allylic ones, though, these ones, the resonance structures will move. We practice that. We'll keep practicing that. That was in workshop number 6. We did some problems like that. We'll keep practicing those. So be careful with the allylic, especially, of that pi bond resonance forming another possible carbocation that might react. Be careful with the resonance structures with these. And anytime you form a carbocation, you got to worry about rearrangements. Got to worry about those rearrangements. And I'll try that next. Right, so here we have this molecule with a benzene ring and a leaving group, and we have it in methanol. So the first question, we got to figure out what kind of reaction is this going to be. So what kind of alkyl halide do we have? What kind of alkyl halide do we have to start with here? secondary, and just secondary. So does that eliminate anything? Nope. Thanks for nothing. Then we want to look at the nucleophile, or base. What kind of nucleophile or base do we have here? It's unreactive and small. So unreactive for sure makes us think what? We know it's going to be either SN1 or E1. And we see it's small, and that maybe makes us think SN1, right? Now, could E1 happen? Absolutely. SN1 and E1 are going to be like, there's always going to be like a mixture of products. So usually what I would do in a question, I would say, now read directions this is part of reading directions very carefully, right? For the substitution reaction below, for the elimination reaction below. If I say that, I'm telling you what kind of reaction it is. I'm not taking the guesswork out of it at some level, right? So be very careful to read the instructions. Don't get in such a rush, right? Read those instructions. Okay, so SN1 or E1, we're not going to worry about it right now because we're going to get to that same kind of intermediate carbocation, and we're going to do some rearrangements today for these carbocations. Then we'll worry about what the products would be if it was SN1 or E1, right? So let's just do the first step in the mechanism. So what's the first step going to be here? Whether it's E1 or SN1, same first step. What's it going to be? The bromine leaves, right? The rate determining step, the formation of the carbocation. Why is that the rate determining step? So why does it take the most energy and why is it the slowest? Right, carbocations are high in energy, they're very reactive. Why are they very reactive and high in energy? Why are they unstable? The octet rule. So the octet rule is a thing. Carbocations don't have a full octet, right? So saying the octet rule is not the answer. Saying that carbocations do not have a full octet, which makes it less stable and more reactive, and that's why it takes more energy to form it. That's why is the rate determining step. Awesome. Balance my charge. Br minus. If I make a carbocation, what do I need to immediately think about? I need to think about those beta things, sigma bonds 2 bonds away, and I need to think about rearrangements. I'm only going to do a rearrangement if I form a more stable carbocation. So this is where numbering is important. 1, 2, 3, 4, 5, 6. Is there anything 2 bonds away, 2 sigma bonds away from the carbocation that I could move to make a more stable carbocation? Because I'm only going to make a more stable one. I'm never going to go uphill. I'm only going to make a more stable one. So this is a secondary carbocation. So how many hyperconjugation buddies does a secondary carbocation have? This one. How many hyperconjugation buddies? I see 1, 2, 3, and then the unwritten hydrogens are still there. 4, 5, and 6. Right? Sigma bonds 2 bonds away. There's hydrogens here, right? They're just not drawn in. They're there. So I have 6 hyperconjugation buddies. Which one of those buddies can I move to make this more stable, to make a more stable carbocation? Should I move a hydrogen on carbon 1? Or what can I move on carbon 3? The methyl. Does it matter 4 or 5? They're the same. Doesn't matter. So I'm going to do a methyl shift. All right, the 2 electrons in that carbon-carbon bond and carbon 4 are going to go to carbon 2. So that rearrangement. So now, what new bond did I form? What new bond did I form and what bond did I break? I broke a sigma bond. I didn't form a pi bond. Carbon 2 is bonded now to what? Which carbon? Carbon 4. 1, 2, 3, 6. There's 4. There's 5. Where's the plus charge? Where's the carbocation at now? It's on 3. Awesome. Now what kind of carbocation do we have? Pretty good. Could I make a more? So now I still need to look, right? I need to make sure. Let's look for those sigma bonds 2 bonds away. So I could go back to carbon 2. I could move a methyl back, but that'd be making a secondary. I guess I could move an H, and that would make a tertiary, but that's a sideways move, right? What about these 2 hydrogens bonded to carbon 6? Should I have those rearrange? Now be careful. Look at carbon 6. What's carbon 6 next to? Carbon 6 is next to the benzene ring. We'd call this the benzylic carbon. If we could have a carbocation in the benzylic position, is that good or bad? That's good. Why? Because then it could do resonance with the ring. So yes, this is a tertiary carbocation, but if I move this hydrogen over, I'd make a benzylic carbocation, which is better than a tertiary carbocation because this can do resonance, right? This is good. This is stable. But right, we talked about ways to stabilize carbocations. What are the 3 ways to stabilize carbocations? Hyperconjugation, pi bond resonance, and lone pair resonance. Hyperconjugation, while okay, it's not as good as pi bond resonance, right? How many hyperconjugation buddies does this tertiary carbocation have? How many hyperconjugation buddies does it have? Sigma bonds 2 bonds away. How many does it have? 1. Mystery CH is not there. 3, 4, 5, 6, 7, 8, 9. A tertiary carbocation has 9 hyperconjugation buddies. That's why it becomes more stable than a secondary. There's more hyperconjugation makes you more stable. But pi bond resonance is better than hyperconjugation. So what's going to happen? This H is going to shift and rearrange. You're going to break that carbon-hydrogen bond and make a new carbon-hydrogen bond and make a new carbocation. So now where's the plus charge? Oops, 4, 5, 6. Where's the plus charge? Carbon 6. Now, that's a really stable carbocation. It's hard to get much better than that. Benzylic, right? At the bottom, it's the most stable. It's secondary in benzylic, right? Still pretty good. Only thing that could be better would be tertiary in benzylic, and I can't make that happen, I don't think. So you have 2 rearrangements there. Now we can start thinking about E1 and SN1. All right? So now we bring back in, Br minus has been along for the ride, right, the whole way. And then the solvent is also around. So what do you guys want to do? You want to do E1 or SN1? Let's do E1. So we have a carbocation. We're gonna make this an E1 reaction. We need to look for what? Beta hydrogens. What kind of beta hydrogens? sp3 beta hydrogens. How many so if this carbon's the alpha carbon, the one with the carbocation is the alpha carbon. Beta is 1 bond over. How many options do we have? How many? Just the 1, right? There's no hydrogens on this, and if there were, it wouldn't work because what's the hybridization say of this carbon? It's sp2. So it's just gonna be carbon 3. So there's an H on carbon 3. Heck, it's the H we just moved, right? All right, it's the H we just moved. So we're gonna take that beta hydrogen, and we could either use the bromine or the solvent. It's up to you. Which one do you want me to use, bromine or the solvent? Let's use the solvent. There's a lot of solvent around. Let's use the solvent. Solvent's going to take that H, make an alkene. Do I need to worry about being anti-periplanar for an E1 reaction? Nope. Don't worry about anti-periplanar. Don't worry about that. What about, there's only one type of beta hydrogen, so can I choose I can't worry about the more substitute, right? There's only one type, so there's no choice there. What's the other thing I can choose, though, about an alkene? So I can't choose if it's more substitute or not. What's the other part that I'm going to want to have? And what's for the Zaitsev rule? There's 2 parts of the Zaitsev rule. The more substituted part that's not an issue here because we only have one type. What's the other type? What's the other thing we worry about with the 8 steps rule? E and Z, right? The E and Z part, the stereochemistry part. So we want to make the alkene such that the big groups, the higher priority groups, are farther apart. So this alkene, if we did it, the higher priority groups are on the opposite sides. So this is a E alkene. That's also what happens in E alkene. So we want to form more substituted double bond, and we want to make the E alkenes as well. And that's what we did here. There's your E1 reaction. Balance my charge. What else did I make? I made right. Don't forget to also balance your charge and show right the oxygen lone pair took the hydrogen that made the pi bond. So you have plus charged methanol with an extra hydrogen on it. Renumber my carbons. 1, 2, 4, 3, 5, 6. There's your E1 product. All right, so one common error people will try to make is they'll get to this and they'll see, oh my God, there's a benzoic position. I gotta get there. You can't shift. You can only do the rearrangements when they're 1, 2 bonds away. 1, 2 bonds away. So you have to do both steps. You can't all of a sudden have the hydrogen here just jump. You can only do rearrangements 1, 2 bonds away. Look for the hyperconjugation buddies. They can do the rearrangements. If it's 3 bonds away, it won't work. Right? It has to be 1, 2 bonds away. I can't move. The hydrogen on 6 is 1, 2, 3 bonds away. It's too far away. I can't do the rearrangement there. You can get there, but it's going to take a couple steps.